Okay, we've completed chapter 11 in the statistics textbook. In this video, we're going to start chapter 12, which you can see is titled The Regression Line. So what are we talking about in chapter 12? We're already pretty familiar with the regression method and getting any of the points along the regression line. Well, we're going to, in this video, in section 1, we're going to go into more specifics on the actual equation of the regression line and kind of analyze the regression method from that perspective. And then in the next section, we're going to talk about another method for calculating not the exact same regression line as the baseline regression method, but a better one with a lower RMS error. In fact, the lowest possible RMS error. That's what least squares is about. And then in section 3, we'll talk about analyzing if the regression makes sense or not. Okay, but let's get started with section 1. Okay, does education pay? Figure 1 shows the relationship between income and education for a sample of 562 California men aged 25 to 29 in 2005. The summary statistics are shown here. The regression estimates for average income at each educational level fall along the regression line shown in the figure. The line slopes up, showing that on the average, income does go up with education. Okay, so you have educational level and income, and you've got this heteroscedastic scatter plot, which you would think would probably be better to have a, like an exponential regression or something, but you could still do a linear regression, that's fine. Okay, so it says, any line can be described in terms of its slope and intercept. Yeah, so we already talked about this. And as far as the regression line, we know when it comes to the equation of a line, you can have 2 points, and then that's all you need to define the equation, or a point and a slope. Well, we have a point, the point of averages, right? All regression lines have to go through the point of averages. So what about the slope? Well, we know the slope as well. It's r sigma y over sigma x, right? So we can easily get the equation for the regression line. The y-intercept is the height of the line when x equals 0, and the slope is the rate at which y increases per unit increase in x. Slope and intercept are illustrated in figure 2. Yeah, so we have the point of averages, okay, and then we have a slope. With a point and a slope, we can use the y minus y1 is equal to m times x minus x1, where x1 and y1 are x average, y average, and m is this. We could fill that in and then expand it out and put it into the slope-intercept form, y equals mx plus b. And the b is going to be the y-intercept, right? Okay, so this is all just elementary stuff from algebra, but yeah, the y-intercept is when x equals 0, because if you have y equals mx plus b, well, when x is equal to 0, well, that's what y is equal to, so that's the y-intercept. So this is just a review of the equations of a line from algebra. How do you get the slope of the regression line? Yeah, take the income education example associated with an increase of 1 standard deviation in education. There's an increase of r standard deviations in income. On this basis, 3 extra years of education are worth an extra. So you do, let's see, how are they getting this? You do, so 3 extra years of education, that's a certain number of standard deviations. I guess that's 0.25, or is that the r value? Let's come back here. So here is the statistics on the scatter plot. Okay, so an extra 3 years of, okay, I see what they did, because an extra 3 years of education is 1 standard deviation. So now you're going to go another 1 standard deviation in the y, but you don't do that. You multiply by 0.25, so it's $6,000 of income on the average. So that's the slope, right? This. We've done this over and over again in the last few chapters. So each extra year is worth $2,000. So yeah, you could do it that way. Well, that's what would happen if you divided all this out. If you did 3 divided by, or no, it would be 24,000 divided by 3 times 1/4, you would get $2,000. That's right, isn't it? 8 times 3 is 24 times 1/4. Yeah. So that's the slope of the line. It's $2,000 per year, right? 1 year of education, $2,000 increase in income. That's the slope. Okay, the intercept of the regression line is the height when x equals 0, corresponding to men with 0 years of education. These men are 12.5 years below average in education. Each year costs $2,000. That is what the slope says. So a man with no education should have an income which is below average by $25,000. His income should be $5,000. That is the intercept, the predicted value of y when x equals 0. 0 years of education may sound extreme, but there were 4 men who reported having no education. Their points are in the lower left corner of figure 1. 3 of these men reported incomes of $20,000, so their points plot one on top of the other. Yeah, so if we come here, we can see there's a couple of these points with 0 years of education. Okay. So, associated with the unit increase in x, there's some average change in y. The slope of the regression line estimates this change. The formula for the slope is this. The intercept of the regression line is just the predicted value for y when x equals 0, which you can get by using the point slope form with the point of averages and the slope, and then putting it into y equals mx plus b form and setting x equal to 0. We could do that. Let's see what they might show us on the next page. I think they do, but you could calculate it, like get an equation for the y-intercept. The equation of a line can be written in terms of the slope and intercept. Yep. The equation for the regression line is called, not surprisingly, the regression equation. In figure 3, the regression equation is, so yeah, there's the slope and, okay, yeah, there's the y-intercept right there. And they calculated this by just, again, they started at the point of averages and they said, okay, how many x units did we go to get to 0 from the point of averages? And then you're going to go down, you just multiply that by the slope to know how far you need to go down for what y value corresponds to x equals 0. Okay, there's nothing new here. The regression equation is just a way of predicting y from x by the regression method. However, social scientists often report the regression equation. The slope and intercept can be interesting in their own right. Yeah, so exactly. We're not doing anything new here. We're just talking about the explicit equation. Like if you were in Excel and you put a linear trend line, and you put the equation up there, that's the regression equation. And it's interesting to think about. We did an example a couple of chapters ago where it looks like the regression equation in Excel was based on the baseline regression method. To me, I would think it would be based on least squares, which we're going to learn can be slightly different than the baseline method. And we'll learn that in the next section. So I'm curious why Excel wouldn't use least squares, because it's more accurate. So just something to think about. Okay, example 1. Education and income for 570 California women aged 25 to 29 are shown in figure 9 on page 192. The summary statistics are, so let me bring that in. Okay, there's figure 9. Here's the statistics. So find the regression equation for predicting income from education. Well, okay, it's just the slope's going to be, so predicting income from education. So this is the y variable, this is the x. Do this divided by this, then times this. That's the slope. Then you could use the point of averages as the point, and then use the point slope formula. Or what they're probably going to do is get the slope and then get the y-intercept by just saying that. So the x-axis is education. So we go 13 years to the left, below average, right? So what does that mean when you calculate the slope? What's the slope? $2,176 per year, right? 0.37 times 20,000 over 3.4. So if you go 13 years to the left, then how far do you need to go down? 13 times this dollars per year. Yeah, 13 times this. And so that's going to be the y-intercept. Yeah, 13 times 2,176 per year. Well, that's not the y-intercept. That's the amount you need to go down below the average. So you get it's negative, right? The average was 18,000, so it's negative. But I mean, that's fine. What they're trying to illustrate here is that you might look at this and say, well, what does this mean? This makes you can have a negative income. Yeah, there's no negative incomes in this sense, unless like you're in debt or something. But no, that's just the equation of the line. You don't want to use the line. You would like state that, okay, the domain of this line only goes up to 5 years of education, but there still is data points over here. So let's see how they explain this. So, okay, we found there's the equation, right? The slope times the input variable minus the y-intercept. So the regression line becomes unreliable when you are far away from the center of the data. So a negative intercept is not too disturbing. Yeah, you just have to, you can't just, I think this is a little bit different. Usually for like a football shaped diagram, you probably wouldn't ever go off the graph, right? You could technically, if we come back over here, what was it? No, that didn't show anything. But for like a football-shaped diagram, you probably could potentially think about using the regression line at any one of the inputs, where here you can't really do that. But even no matter what the case, even for a football-shaped diagram, you need to be careful when applying the regression line outside of the middle, when there's like sparse data points and there's a lot of random chance occurrences. Okay, so what was part B? Use the equation to predict the income of a woman whose educational level is 8 years, 12 years, 16 years. So, okay, wait, what was 8 years, 12 years, 16 years? So we can do this, and it's just, you just plug it in, plug in the input. And that's what they do, and they get these different income levels. And again, we're in the middle of the diagram, so it doesn't mean we can trust these predictions, but at least we can trust that as far as that regression line goes. Those are what the regression line is saying with respect to that scatter plot. This completes the solution. Despite the negative intercept, the predictions are quite reasonable for most of the women. Yeah, but you could argue that this should be modeled with an exponential. Even the exponential could account for all of these points, right? Exponentials never go to zero. So, okay, in example 1, the slope is $2,176 per year. Associated with each extra year of education, there's an increase in that much in income on the average. The phrase associated with sounds like it is talking around some difficulty. And here is the issue. Are income differences caused by differences in educational level, or do both reflect the common influence of some third variable? The phrase associated with was invented to let statisticians talk about regression without having to commit themselves on this sort of point. Absolutely. We've talked about in previous chapters on regression and correlation how so you have the correlation coefficient measures association, the level of association, right? And we've talked about how association and causation are not the same thing. You can have association, and there is 100% an association, but when you analyze causation, it can be completely ridiculous. Like we looked at if you had shoe size of children versus their score on some like standardized test. Right? There was an association between shoe size and their score on the test, or it was reading skills. There is an association, 100%. But when you think about the causation, it's silly. It's just because the students are getting older. They have bigger feet, right? But the key point they're making here is that you can be really flexible with the word association. When it comes to using the word association, you don't have to think about the logic behind it if the association makes sense. Is there an association or not? Right? Is there some pattern with, look, as this variable goes up, that variable goes up. Now, why is there an association? Maybe there's confounding variables, maybe there aren't. Who knows? Doesn't matter. You don't have to talk about stuff like that when you're using the word association. So they're saying that, yeah, so there is an association. What they're saying is there is an association here between educational level of women and the income. Was this just women? I think so. Yeah, there is an association, clearly, in income level, right? But what they're pointing out here is that are income differences caused by differences in educational level, or do both reflect the common influence of some third variable? Doesn't matter. The phrase associated with was invented to let statisticians talk about regression without having to commit themselves on this sort of point. Okay, the slope is often used to predict how Y will respond if someone intervenes and changes X. This is legitimate when the data come from a controlled experiment. With observational studies, the inference is often shaky because of confounding. Look at example 1. On the average, the women who finished high school, 12 years of education, earned about $9,000 more than women who just finished middle school. Okay, so, well, okay, let's keep reading. Now, take a representative group of women with 8 years of education. If the government intervened and sent them on to get high school degrees, the slope suggests that their incomes would go up by an average of $9,000. However, example 1 is based on survey data rather than a controlled experiment. One group of women in the survey had 8 years of education. Another separate group had 12 years. The two groups were different with respect to many factors besides education, like intelligence, ambition, and family background. The effects of these factors are confounded with the effect of education and go into the slope. Sending people off to high school probably would make their incomes go up, but not by the full $9,000. To measure the impact on incomes, it might be necessary to run a controlled experiment. Many investigators would use a technique called multiple regression. More about this in section 3. So, yeah, what they're saying is that if what you could do is you could take the slope of a regression line and kind of think about how, all right, this is telling me if I nudged the input in one direction, let's say, then it's going to change the output by this amount, right? You can kind of think about it that way. But they're saying you don't really want to do this unless it's a controlled experiment, because there's too many confounding variables when it comes to observational studies like these. So they're suggesting that even if this was modeled with an exponential curve, and you could kind of think about at any point on the curve, if you nudged in one direction, what would the change be? They're saying that you can only go so far with how applicable you're taking the curve fit to be. That's how I'm understanding this. They're saying that, like, you know, when it comes to controlled experiments, let's say you have a controlled experiment with a lot of data points, then you have a lot more power to say, okay, if I brought in a new data point, what's going to happen, right? That's kind of what they're doing here. They're thinking about, okay, what does this regression line tell us? They're saying, okay, if you have controlled or observational study data and you put a regression line or some curve fit through it, and you can't look too deep into the meaning of that regression line, because observational studies have more confounding variables, as opposed to with a controlled experiment. If you have with a good amount of data points, if you have a curve fit going through it, you can really think about, okay, this curve fit is like a representation of, it's like a characteristic of this data, right? You can start to think about, well, what if I nudged a little bit in this direction, what's the slope tell me is going to happen? Right? But they're saying you can't really do that here. It's like saying if you looked at this and said, like, so the government's gonna intervene and send off a big group of women to get high school degrees so you can increase the income level. And they're going to increase it. They look at it and say, we're going to increase this by on average $9,000. That's what the slope of the line tells us. Well, there's too many confounding variables. You don't, with observational studies, you're not putting people into the treatment and control groups. You're not deciding on that. So you don't know, those women could be less ambitious and they're not going to do anything. You see? Okay. With an observational study, the slope and intercept of the regression line are only descriptive statistics. They say how the average value of one variable is related to values of another variable in the population being observed. The slope cannot be relied on to predict how Y will respond if you intervene to change the value of X. Right. So in general, with an observational study, you have the slope and intercept of the regression line. They're just these descriptive statistics. You can't really go so far with making predictions for data points that aren't a part of the original set of data points that you calculated the slope and intercept with, as you could with a controlled experiment. They just say how the average value of one variable is related to another variable in the population being observed. Right? The slope cannot be relied upon to predict how y would respond if you intervene to change the value of x. Right? So you're altering the data set a little bit. You're trying to predict, in a sense, what they're saying is you're trying to predict what happens with future data points that aren't part of the original algebra to calculate the slope and the intercept. So if you run an observational study, the regression line only describes the data that you see. The line cannot be relied upon for predicting the results of interventions. Right, because of the confounding variables. You look at the chart and say, well, here's the regression line, here's the curve fit. Well, that curve fit's telling me if we did this with these data points, then we would get this kind of change in the results. You're changing the data points, but there's too many confounding variables for you to use the curve fit to look that deeply into the underlying meaning of the data that curve fit is applied to. Okay, there is another assumption that we have been making throughout this section, that the average of y depends linearly on x. If the relationship is nonlinear, the regression line may be quite misleading, whether the data come from an experiment or an observational study. Okay, so this is an interesting statement that they're making here. They seem to be suggesting that if you have a well-controlled experiment, then you're going to expect that data to be football-shaped or apply to a linear regression. And I'm not sure if that's what they mean. I mean, you could have an experiment that's a well-controlled experiment where you find data points are like exponentially distributed, so that can't be what they mean. I guess maybe they're saying that for some data that you potentially would expect to be football-shaped or linear, and it ends up not being, that might tend to happen for cases where you're dealing with an observational study and there's confounding variables that are pushing it away from the football shape. So what they're saying here is we've been making an assumption that so y depends linearly on x. To me, what they're saying is that you still need to, if you're going to be doing regression, linear regression, you're going to want to check how well of a football shape you're dealing with, right? That's something we're probably going to want to look at. And it makes sense from this standpoint. This is going to be, we should do exponential here. Okay, but again, we've been kind of making the assumption that when they say y depends linearly on x, we've been making the assumption of like a perfect football shape. Now, if it wasn't a perfect football shape, does that mean we're not going to use linear regression? Well, no, I guess it needs to deviate from the non-perfect football shape to a certain extent. Then we might decide to go to something else. But still, though, we still need to understand what any deviations from the non-football shape mean for our linear regression if we're still going to use it. So it's just some stuff we need to think about and learn. And we're going to talk about this more in I think in section 3 and in more advanced classes. Okay, let's go through these exercises. For the men in figure 1, the regression equation for predicting average income from education is shown here. Okay, so figure 1. Okay, so there's figure 1. Now, predict the income for one of these men who has 8 years of schooling, 12 years of schooling, 16 years of schooling. So just plug it in to the regression equation. All right, so we've got 2,000 times 8. I mean, we can do this. 2,000 times x plus 5,000. Okay, so do this with x equal to 8. Do this with x equal to 12. And with x equal to 16. 21,000, 29,000, 37,000. Okay. The International Rice Research Institute in the Philippines developed the hybrid rice IR8, setting off the green revolution in tropical agriculture. Among other things, they made a thorough study of the effects of fertilizer on rice yields. These experiments involved a number of experimental plots of about 20 square yards in size. Each plot was planted with IR8 and fertilized with some amount of nitrogen chosen by the investigators. The amounts ranged from 0 to about a pound. When the rice was harvested, the yield was measured and related to the amount of nitrogen applied. In one such experiment, the correlation between rice yield and nitrogen was 0.95, and the regression equation was as shown here. Okay, so they just gave us a backstory here, but it all comes down to they're saying that when the rice was harvested, the yield was measured and related to the amount of nitrogen applied. In one such experiment, the correlation between rice yield and nitrogen was 0.95, and the regression equation was this. So an unfertilized plot can be expected to produce around how much rice? Unfertilized. Okay, that's the y-intercept, right? 240 ounces. That's if there's no nitrogen. So there's the y-intercept. Each extra ounce of nitrogen fertilizer can be expected to increase the rice yield by what? So what's the slope of the regression line? It's here. 20 ounces of rice per nitrogen. 20 ounces. Predict the rice yield when the amount of fertilizer is 3 ounces of nitrogen, 4 ounces of nitrogen. So, okay, that's just, you just plug it in. So, okay, we've got 20 times 3 plus 240, then 20 times 4 plus 240. So 300 and 320. Okay, 300 ounces, 320 ounces. Okay. Was this an observational study or a controlled experiment? Okay, so let's see. What's the key features that make something observational versus controlled? It's, are you choosing what goes into the treatment and control groups? Then it's controlled. Otherwise, it's observational. So are they? Okay, so thorough study of fertilizer effects on rice yields. These experiments involved a number of experimental plots, 20 square yards in size. Each plot was planted with IR8 and fertilized with some amount of nitrogen chosen by the investigators. Yeah, so I mean, this is controlled. They're not like studying if some farmer had put fertilizer out there and in their field, and they're just looking at the data. The farmer just randomly put fertilizer out, but different farmers between their fields maybe. They're not controlling who put the nitrogen in what fields and in the specifics of the different plants that are being fertilized and not being fertilized. That would be observational, but this is fully controlled, so controlled. Right, they're separating out the different plots. They're choosing what they want to plant in which plot and which plots are going to be fertilized. It's fully controlled. In fact, fertilizer was applied only in the following amounts: 0 ounces, 4 ounces, 8 ounces, 12 ounces, etc. Would you trust the prediction for 3 ounces of nitrogen, even though this particular amount was never applied? Yeah, sure, absolutely. I mean, assuming there's enough data points. I mean, it doesn't sound like that extensive of an experiment, but I think what they're asking here is, let's say you had some fully controlled experiment with a lot of data points, but you still can't, actually apply every single input that's like possible. Usually you can't, right? Like you could do 1 ounce, 2 ounce, 3 ounces, 4 ounces, but what about 3.5 ounces, 3.25 ounces? And so the question is, well, if you didn't actually apply that specific input, can you use the regression equation at an input that you didn't actually apply? Sure, you can. Again, assuming there's enough data points and you feel like it's a quality regression. So yes. Would you trust? Yes. Would you trust the prediction for 100 ounces of nitrogen? Okay, well, yeah, but a caveat here is that assuming you're also in the middle of the regression. So no, in this case, no, because once you get too far out from the middle of the data, then you have to be careful. So I'm assuming that's what they're talking about here. Yeah, that's got to be what they're talking about. This is going to be potentially on the outskirts. I mean, we really need more information to say if 100 ounces is for sure on the outskirts of the study. Oh, well, okay, it says the amounts ranged from 0 to about a pound. Okay, so 1 pound is, 0 ounces, 4 ounces, 16 ounces. 1 pound is 16 ounces, so 100 ounces, that's too far. Okay, summary statistics for heights of fathers and sons are on page 170. All right. Here we go. There's the statistics. Find the regression equation for predicting the height of a son from the height of his father, and find the regression equation for predicting the height of a father from the height of his son. Okay, so in both cases, we're going to have the same slope. The slope is going to be, because the standard deviations are the same, the standard deviations dividing those, you get 1, and then you multiply by r. So the slope is going to be 1/2 for both of these equations, okay? Now, for predicting father's height from son's, where do we start here? Son's height from father's height, then we look at the point of averages as the x is the father's height, and the y is the son's height. So now we have a point and a slope. We can just do so. Okay, we're predicting, we've got y minus y1 is equal to m times x minus x1. So y is equal to 1/2 x minus 68 over 2 plus 69. So let's see, minus 68 over 2 plus 69 is 35. So y is equal to 1/2 x plus 35. So where x is the height of the father and y is the height of the son. Now for the second part, we just switch these. Usually the slope is going to be different, but it's just a special case where it's not. Because if the standard deviations were different, then we'd have to adjust the slope. But here we're just going to have, now the sons are the input and the fathers are the output. So, okay, y minus y1 is equal to m times x minus x1. So y is equal to 1/2 x minus 69 over 2 plus 68. So we've got minus 69 over 2 plus 68. So what is this? 33.5. So 1/2 x plus 33.5. And this is the son's height is the x and father's height is y. Okay, an expert witness offers testimony that regression is a substitute for controlled experiments. It provides a precise estimate of the effect of one variable on another. No. That's what we just talked about at the end of this section. It is absolutely not a substitute for controlled experiments. If you've got an observational study, you can use regression to just describe those data points in front of you. What they're suggesting here is that you can use, if instead of doing the controlled experiment, you could use observational study data, do regression, and now use that regression line to predict things that are going to happen outside of those main data points. No,